All right. So, what is a generator and how do you get to the finite elements of a matrix Lie group? So when I say matrix Lie group, what I mean is that it's a continuous group. Okay. So that means that there are some parameters which are not discrete parameters, some continuous parameters. And if there are some continuous parameters, they take value in some space, some manifold. Okay. A manifold is something which locally looks like Rn. Okay. So the parameter space is locally Rn. Okay?
Yeah, makes sense.
Right. So the idea is, so there is some identity element, right? And, for the matrix group, for the matrix Lie groups, the identity element it'll just be the identity matrix, right? Will be 1, the identity matrix, because for us, for the matrix Lie group, the matrix multiplication is the group multiplication, right? And the unique matrix which leaves all the elements the same under multiplication is the identity matrix. So, right? So now, we want to say, what is the notion of, say, smallness, right? So, because we are looking at a group which is also manifold. So there should be some corresponding in a manifold. If you have, suppose you have some manifold, and we are looking at some neighborhood here, which we have mapped to neighborhood in Rn. Okay, that's what we mean by manifold, that for every neighborhood, there is some map which takes you to some subset of Rn, right? Suppose we're looking at the neighborhood of what we are calling the identity, right? Or, maybe it's better to call it, right? So this maps to, say, this point over here, and there is a notion of like a very infinitesimal neighborhood here, right? Because we're dealing with a manifold. So now I can ask, what do the elements in this little neighborhood look like? Okay, so those elements will be the identity matrix plus, if the dimension of the manifold is, say, D, if the dimension of the group, say, we have the dimension of the group is, say, D, and then there are, D independent parameters we can choose, right? And so this means that we are choosing them in such that, it's very, these are small parameters. Okay. So Saib, do you agree that this would be the form of a group element, which is in the infinitesimal local neighborhood of the identity operator or identity matrix?
Yeah, I could see that.
Right. And of course, we're using Einstein summation convention.
Sir, I had a question here.
Yeah.
So this is a group in terms of matrix multiplication, right?
Yeah.
So we are incorporating the notion of addition here.
Yes, because it's a matrix, right? I'm just doing matrix addition, matrix expansion.
Oh, okay.
G is a matrix, so yeah, this is all the things that we take granted for matrices are there.
I do have
I
one
get it.
question,
Yeah,
which is that, so is in some sense the xi the possible directions of this manifold, like we're adding a little bit in every direction?
exactly. You know, the alpha i's will determine which direction we're moving in.
Okay.
So that's exactly, so xi's, what they do is that they tell you what directions there are, orthogonal directions there are in the neighborhood of 1. Right? This is x1, this is x2. Right? Is that clear?
Yes.
Yeah. So these xi's, which tell you, they're essentially the directions, if you do some differential geometry, they are called tangent vectors. And they are what we are calling the generators. So you can take this as the definition of the generators. Okay.
Yeah, I'm
So
good so far.
Okay, good. All right. So now, the generators that you write down will depend on what represent, how you're parameterizing your group, right? So depending on, so for example, in 3 dimensions, we can parameterize rotations in many different ways. There's a very famous parameterization called the Euler parameterization. I haven't really gone into those. Usually they're taught in classical mechanics and places like that. So depending on the parameterization, the form of the generator will be different. Here we are not really going to deal with those subtleties. But now, if I ask you the question, or if you ask the question, okay, so this generator is, suppose we take x1, and what is x1? x1 is a vector which is tangent to this point, right? So if I look at it from the side, our manifold is, our group is some manifold, and this point is, say, 1, and the generator is giving me a direction that is tangent to that point. So I'm just looking at this from the side. Now, I can ask the question, what if I keep moving in that direction little by little, right? Here, we have moved by a small amount in this general direction. Okay, so we can say, what if we keep moving in that direction by that small amount, and we keep on moving many times, so that we are far away from the identity. So in other words, so we are basically moving, let me use a different color, moving in that direction. So, and we say reach this point, let's call that point P. And on this, on this manifold, P would be somewhere over here. So this would technically not be P, but it should really be the coordinates of P, right? So how do we find this point? Well, how do you find the group element that corresponds to P? So this is, let's call it a GP, because it's also a group element, right? And there we do what is known as exponentiation. So what we say is that, well, we had a very small map, a very small group element, say delta of G, and this was given by 1 plus delta alpha I of x of I. Now, what if I take this, apply this n times? Okay. And now let's define a finite angle, a finite parameter, set of parameters, which I'm calling alpha I. There is divided by n. So I'm defining alpha I to be given by delta alpha I times n. Okay. Now, what happens in the limit where n goes to infinity, but I'm keeping this fixed, alpha I fixed. Okay. So we have 1 plus alpha I n x of I. Of course, this is a dot product to the power n, and n is going to infinity. And this we know is e to the power alpha I xi, right? This is also something that holds for matrices, not just for numbers. So this is an example of a finite element. And the geometrical interpretation of this is that we have gone some finite distance from our identity over here. So this it represents G of alpha. So Saif, does that clear up the notion of how this is how these two ideas are interrelated?
Yeah, so one follow-up question, which is, so if two elements are continuously connected, that means you were saying that like you have to go there gradually, but that means that the gradual steps are also all inside the manifold, right?
Exactly.
Like with the parity matrix, the reason it's not continuously connected is because the in-between steps wouldn't be on the manifold.
Exactly, exactly. For parity, what happens is that, so you have, say this is SON, this is SON, and this is the identity element, and this is the part of ON. So parity takes you to minus the identity element, right? And these two together give you ON. Okay, so parity, there is no there is no continuous parameter that one can associate to parity. It's a discrete transformation. It's an on or off switch.